I'm Sawyer and this is the wooden bridge I designed and cut for Physics 12. In this video, I'll walk through how my bridge works, the physics behind it, and why it's built the way it is. I'll cover things like force, torque, compression, tension, and stability. Let's start with the structure. My bridge uses a truss design, which means it relies on a series of interconnected triangles to spread out force efficiently. Like this. Triangles are key in engineering because they are inherently rigid and strong. When force is applied, they don't distort easily. Each diagonal and vertical member works together to distribute the load from the center, which is where the weight will go, towards the supports at either end. This helps prevent any one piece from carrying too much stress. When a load is placed on the bridge, gravity pulls it down. That creates a downward force on the top two beams of the bridge, called the deck. In this case, I'm applying the force right in the center of the bridge. This is where the structure is designed to be the strongest. By applying the force here, the load is split evenly between two sides, and the force is distributed symmetrically through the truss. The top horizontal members experience compression, which is a squishing force. The bottom horizontal members experience tension, meaning they're being pulled apart, like that. The diagonal and vertical members help support this by managing both compression and tension depending on their angle and position, like those ones. Another important concept is equilibrium. For the bridge to hold still and not collapse, all the forces need to balance out. So the sum of the upward forces equals the sum of the downward forces, which is F net equals 0. Okay. Let's talk about torque, which is rotational force, like this, or like this. If there's more weight on one side than the other, or the bridge isn't supported evenly, torque is created around the support points. Those, a whole bunch of these. This can cause twisting or rotation, which can lead to failure. The design I used keeps the load centered, and the force is symmetrical, minimizing torque. The flat base and strong joints reduce any chance of the bridge rotating or twisting under stress. Stability was a huge part of my design. By laser cutting the wood and designing it myself, I made sure the connections were extremely precise. This keeps the joints tight and avoids weak spots where torque or bending could cause damage. Also, notice how the triangles are layered in a way that supports both the top and the bottom of the bridge. This adds structural redundancy, which means if one part starts to fail, the rest helps to pick up the slack. The bridge's center of mass is low and centered, which also helps with balance and stability. Center mass. In summary, my bridge uses physics principles like force, distribution, compression, tension, torque, and equilibrium to stay strong under the load. Using triangles and symmetry was key to making the structure efficient. By understanding how different parts of the bridge respond to different forces, I was able to make something lightweight but still stable. Thank you.
Hi there, my name is Sawyer Palmer, and in this video, I'm going to talk about what happened when my bridge broke during the testing. I'll talk about how I designed, just a little bit about how I designed it, where and why it broke, and what I can improve if I were to do it again, including a quick comparison. So I designed and laser cut my bridge as a wooden truss bridge to go underneath the testing. I applied the load at the center right here on this middle horizontal beam, and even though the force was applied in the middle, it didn't break in the middle, it broke on the edge, and it might seem surprising, but it makes a lot of sense if you think about how forces move throughout the bridge. When you apply a downward force on the center of the bridge, the structure won't just resist it at that one point. The force would travel throughout the truss system, especially towards the two ends, which act as the bridge's supports. So even though the middle takes the initial hit, the edges would carry a lot of the stress, which is why my bridge broke right here, because it was one of the weakest parts of the bridge and one of the most important ones. The part of my bridge that broke was experiencing a combination of probably shear force as the bridge was pushed down and the supports were pushed back up, compression, especially in the angled truss parts, like the angled ones, and possibly even torque if it wasn't perfectly flat or if it was a little bit asymmetrical. And if the joint near the edge was slightly weaker or slightly miscalculated, or again, not the same as this side, then that would have been a huge factor in the breakage on this side of the bridge. If I were to redesign my bridge, there are a few things that I would change. I would reinforce or change the joints near the supports, so on these sides, and because that's where the load ends up, so I would either make it go up or change it entirely by flipping it and doing one above the top, because these ones are hard. The under the table bridges would be hard to keep the edges from breaking. And I would improve the load distribution by adding more vertical or diagonal members between the center and the ends, so up here, around here. And I would make 100% sure that both ends are perfectly flat on the testing table to prevent any twist or extra strain on the bridge. And these small design changes can make a huge difference in how the forces that are spread throughout the bridge are actually being applied to the bridge and where the failure would happen. So I'd compare my bridge to a completely different type of bridge created by Stuart Coach. He did an arch type of bridge, which would redirect the load outward towards the supports, which is similar to mine, except his was all the way in, and it would reduce bending and shear in the horizontal pieces. His design was more efficient at handling compression, and that was probably what helped it survive longer. My bridge relied on flat trusses, which are strong, but they don't naturally redirect the forces the same way that arches do. So in a future version, I would incorporate some arches into my bridge. Even though my bridge failed, I learned a lot about how forces can travel through a structure, even if it's a tiny one, and how minuscule design choices like joint strength or simple geometry can make a huge impact on something such as a bridge. Thank you.